You might think of geometry as something permanently confined to a dusty chalkboard or a high school textbook, but the truth is, it's literally the invisible scaffolding of our reality. Welcome to This Explainer. Today, we're going to unlock the power of one very specific, foundational shape that dictates exactly how our universe is built.
To start off, I want you to just visualize the everyday structures you interact with. Don't worry about numbers or equations right now. Just look around the room you're sitting in, think about the building you live in, or even the streets you walk down every single day. There is this hidden architecture right under our noses, working tirelessly to hold things together, distribute weight, and just make movement possible.
Think about it. From the skateboarding ramps we slide down to those heavy steel trusses holding up massive suspension bridges, a very specific geometric shape is constantly at work. You see it when you lean a climbing ladder against a wall, creating that angled path. You see it in the taut, wind-filled sails of a boat cutting through the water. You even rely on it when you grab a stair banister as you're walking up to your bedroom.
Now, that raises a pretty fundamental question. What is the actual connection between a boat sail and a roof truss? Why do completely different structures, designed for totally different purposes across thousands of years of human engineering, all rely on the exact same hidden angles? What invisible mathematical rule unites the carpenter, the sailor, and the bridge engineer?
Section 1. Hidden in plain sight.
Section 2. The universal equation.
To really understand the magic of this foundational shape, we've got to speak its language. The absolute crucial starting point is defining the hypotenuse. It's a term we hear a lot but might easily have forgotten since our school days. But this is the star of the show. No matter how you rotate or flip a right triangle, the hypotenuse is always the longest side, and it's always staring directly across from that perfect 90-degree corner. It's the ladder leaning against the wall, it's the slide on the playground.
And we have to make a clear distinction between the hypotenuse and the other two sides, which we call the legs. Just to ground us in the basic anatomy here, the legs are the foundation. They're the floor and the wall that meet to form that perfect 90-degree corner. The hypotenuse? That's the bridge connecting their outer endpoints. Understanding this exact relationship is literally what gave ancient humans the power to build empires.
Because of this simple, profound formula, a squared plus b squared equals c squared. It dictates that the areas of the squares on the two legs equal the area of the square on the hypotenuse. You probably know it as the Pythagorean equation. If you take the length of leg A and physically draw a square off it, and then do the exact same thing for leg B, the total area of those two squares will perfectly, flawlessly equal the area of a square drawn off the hypotenuse, c. It's like this beautiful cosmic balancing act that never fails in flat space.
The most famous, pristine example of this equation in action is the 3-4-5 triangle. This is a cornerstone used by builders for millennia. If you have a leg of 3 units and a leg of 4 units, the hypotenuse is always going to be exactly 5 units. 3 squared is 9, 4 squared is 16, and together they make 25, which of course is exactly 5 squared. Ancient surveyors used to actually tie ropes with knots at these exact intervals just to guarantee perfectly square corners for their temples and pyramids.
Section 3. A global discovery.
Okay, it is time to bust a major historical myth. This mathematical rule actually predates Pythagoras himself by over 1,000 years. This discovery was a truly universal human pursuit across Mesopotamia, China, and India. The Babylonian Plimpton 322 tablet recorded these triples way back in 1800 BC. Over in China, the Gugu theorem reasoned this math out by 1100 BC, hundreds of years before Pythagoras was even born. In India, around 800 BC, the Shilpa Sutras used it to construct intricate fire altars. So Pythagoras might have popularized it in Greece around 570 BC, but he was incredibly late to the party.
Section 4. Triangles within triangles.
Now, right triangles hold these hidden structures inside themselves. They have this slightly mystical property where they can endlessly replicate their own proportions, almost like mathematical DNA. By stepping through the altitude on hypotenuse theorem, we can see that dropping a single perpendicular line creates a beautifully proportional geometric puzzle. If you draw a line straight down from the 90-degree corner to the hypotenuse, forming another 90-degree angle where they meet, you instantly create 2 miniature right triangles inside the big one. And here's the genius part. All 3 of these triangles, the big one and the 2 small ones, have the exact same angles. They are mathematically similar, perfect scaled-down clones of each other.
And what's absolutely fascinating is that U.S. President James A. Garfield actually published an elegant algebraic proof for this theorem using a trapezoid. Yeah, you heard that right.
Before he was the 20th president, Garfield was a U.S. representative who just played around with geometry for fun. He arranged two identical right triangles so they formed a trapezoid and used basic area calculations to prove that a squared plus b squared equals c squared. It just brilliantly illustrates how accessible and universal this math really is.
Section 5. Beyond two dimensions.
But here's the thing. This mathematical magic doesn't stop at flat, two-dimensional surfaces. It scales up dramatically into the three-dimensional universe we actually live in. This single simple shape forms the mathematical foundation for calculating distances in 3D solid geometry, complex numbers, and trigonometry. If you want to know the exact diagonal distance from the bottom left corner of your room to the top right corner on the ceiling, you just apply the Pythagorean theorem twice. It translates seamlessly into the Euclidean distance formula used in computer programming, finding absolute values in complex math, and it literally underpins the fundamental identity of all trigonometry.
You can even zoom out into higher dimensions, and the core Pythagorean logic perfectly adapts. In a 2D plane, it's a squared plus b squared equals c squared. In 3D space, you just add a third dimension, the depth, so it becomes a squared plus b squared plus d squared. Mathematicians even use this exact same framework in n dimensions to calculate the sum of squares of orthogonal vectors. They're using this to map hyperdimensional space, dimensions our human brains can't even easily visualize.
However, there is a boundary to this rule. If you try to map a right triangle onto a curved sphere, the standard equation actually breaks down. This flawlessly illustrates the limits of Euclidean geometry, which only operates on flat planes. If you draw a massive right triangle on the surface of the Earth, say starting at the North Pole, going straight down to the equator, across, and back up, the sides actually curve. Because the surface isn't flat, spherical geometry takes over and the math changes. A squared plus b squared suddenly gives you a number larger than c squared.
Which leaves us with a totally mind-bending question to conclude this explainer. If the Pythagorean theorem governs flat planes and 3D space, how do the rules of mathematics adapt when the very fabric of the universe is curved? Einstein showed us that gravity actually warps space and time. So out there, near a black hole or a massive star, the right triangles that built our bridges and calculated our dimensions suddenly bend to an entirely new set of rules. It makes you wonder, doesn't it? What other hidden geometries are waiting out there for us to discover? Keep looking at the angles around you, and I'll catch you in the next explainer.